I just want to thank everyone for allowing my team and I to give a short presentation on some of the work that we started doing actually at the conference last year in Oak Ridge National Laboratory. I feel like I'm at a disadvantage. My formative years were in the South. We didn't learn to talk fast there. So I'll be watching Mark's head movements. You did it? Okay. Lynn User and I spent a little time in Bulgaria this past summer. When I think of head movements, I'm always thinking of, that's the one thing I just couldn't get. The language, the Cyrillic, the food, that was all fantastic. But the head movements in Bulgaria means no. Yes, I never could get that. The concept that I'm going to talk about today in the short 5 minutes is the cartographic modeling language. And if you're from the GIS community, particularly if you're a geographer, you know the cartographic modeling language. You've used it because you took that in your advanced GIS class or your modeling class, and you're familiar with it. If you're probably from computer science or computer engineering, you may not be familiar with it, but you're probably familiar with some other prototypical language that's domain specific in your area. The focus in the next few minutes is going to be on the CML, the cartographic modeling language. The Flux footprint modeling, I'm just going to give you a little bit of information about it because it serves as a context for the problem. Okay? It really isn't, the goal here. Okay? I'll talk a little bit about more about tonight at the poster session and tomorrow. I feel like this project really is the kind of thing that we want to do. Is we got together last year because April and I had a problem. It's always one of those things where your colleague says, she's a micrometeorologist, by the way, she says, I got this problem, I think it's spatial, can you do it? And I said, yeah. In fact, we could have your student do it because she's in my modeling class. That's Sarah Fletcher. And so she described the problem, and I said, yeah, that's pretty simple. We could do that, not a problem. That's always what you shouldn't do, say, yeah, we can do it. This is an area in southern Louisiana where they burn sugar cane. Sugar cane has a lot of effluent, one of which is ammonia. There's other sources of ammonia as well. And so what they're trying to do is to come up with a modeling approach for quantifying the location of ammonia sources from different locations, particularly like schools and other areas of health risk. And so she was gathering 12-hour samples of ammonia data at this location. And what she wants to know is, where did the ammonia come from? Okay? Well, a 12-hour sample, that's how long it takes to get an ammonia sample as opposed to a really small amount of time. So her method of doing this is to also sample the meteorological data. That's the air movements and atmospheric parameters, the micrometeorological parameters like temperature, humidity, and so forth. She gathers this data at 10 hertz. It's 10 times a second. Okay? So we're expected to take equivalent of 500,000 observations, integrate that together to represent her 12-hour sample of ammonia concentration. And to me, I can't do this on my desktop. Okay? And I said, April, suppose we do this, we create a spatial distribution of the sources of ammonia, how will we know that we're even got the model implemented correctly? And her answer was, well, I don't know. We've never seen a map of the spatial distribution of ammonia concentration sources. Okay? So in the micrometeorological community, they use something called footprint models, which has been around for a long time to solve that problem. Well, that problem was on my mind when we got together at Oak Ridge National Lab last year. And I met Yan Liu. He integrated with Sarah Fletcher. It's what you're supposed to do, integrate with people. And the students met with each other, had a good time. Shawan had the idea, we can solve this problem. Okay? And he committed his talent here to probe that. And Babik, who you've heard from already, and Kumar and Anand, who you also have heard from, they've each have played a major role in putting in an implementation solution for this project. Okay, I'm going to show you an equation. Those of you who are familiar with Gaussian diffusion models, you're going to know that's a familiar Gaussian type of equation. And what it does is predict the probability that the source of the ammonia came from some distance downwind. So this is one-dimensional as opposed to a true 2- or 3-dimensional model. It's one-dimensional, and how it's used in the past is you generate the Gaussian curve, and you take the spatial distance downwind from the receptor location, you take the highest point. Well, you've immediately thrown away all the other probability information by doing so. And so I said, well, wait, we could take this, we could generate this for every single meteorological observation. We could integrate them together if Shawan could help us, and he did. Okay? So how would I do this, or how would a student who's a geographer or GIS analyst? Well, you can look at an equation, you immediately go and say, okay, where are the spatial components? Where are the local focal zonal operators? You see, okay, Z is a downwind distance. That's a focal operator. So you separate out all the operands and operators into cartographic modeling procedures. At least that's what we do in GIS. Okay? And then you implement it. And the implementation strategy over the years has obviously changed. It used to be, those of you who know what that means, you don't want to. Okay? EML, that's the third-ass flavor of it. Python is what we use today. And if you were going to use this in the gateway, you'd use PHP, right? I'm arguing that the cartographic modeling language, if we're going to implement and take a strategic move towards putting all the spatial operators in some type of CyberGIS approach, it's as good as any right now. It's not perfect, it's good as any. It's widely accepted in the GIS analyst community. The big players in the GIS software industry have integrated it. Dana Tomlin was one of the contractors in the early 90s to see that they did so. And we teach it in our educational settings. And for those of you who aren't familiar with it, it's basically, you can boil it down to three major categories: local, focal, and zonal operators to solve problems. It's been extended since it was originally conceived by Barry and Senton and Tomlin. Since then, there's been some work by Karen Kemp, who you know, and Li Xingyong for allowing vector data types to be input to it. It doesn't do everything. It doesn't conserve mass, momentum, energy. There's no operators for doing that in there. Okay, but we maybe could extend it. Okay. It's analogous to the SQL, which everyone's familiar with in relational database management systems. Okay, it doesn't matter whether you're using Oracle or SQL Server. You know, SQL is SQL. Okay. There's different ways of implementing a model inside of GIS, either embedded or you can couple it. Some different expressions is using a graphical user interface. We've seen that several times today. A Python scripting approach, which is the common way today. Not too many years ago, a couple of years ago, we used to use VBA. Before that, it was C++. Before that, if you're wearing reading glasses, it's Fortran. Okay? Model builders is a common approach that we use today for small models, and then we can use tools. Okay? Here's an example of a model builder that I have my students implement the Aloha air diffusion model in class all the time. And that's all you need to do it, put the whole Aloha model together. And so this is the Graniteville release of a chlorine concentration that actually occurred, you know, not too many years ago. But that's how you would express it. Students know how to do this. Okay? The GIS community knows how to do this. And so I'm suggesting that's the approach that we should take. Okay? So from a user's perspective, if we want to get access to the geospatial data and the geographic operators, we don't want to reprogram, write distance, direction, cost distance operators again. So we have to use some approach. And the way we do that is use a library. How do we access it? Through a programming language, through a scripting language, and through some type of interface. And we've got one CPU that we can run it on. So I can't solve April's problem, 500,000 operations. So we use multiple CPU, but I don't have a solution to get access to those. Okay? Another approach, you saw Mike talk about this today, was the graphical model. I showed you an example of Model Builder. It's called Model Maker inside RDAS. If you're familiar with Stella, if you come from the physical science community, you may not know this, but the person who's the architect, he was one of the architects of Model Maker and Model Builder, Perry Lautenschlager. We stole him from Stella, okay, and he helped put the Model Builder and Model Maker together at RDAS, and then later Esri took it from RDAS. Okay, this is what we're doing right now in our project, okay, and I'm going to rely on my colleagues in here to, if I go much further in describing the details here. The GIS user is going to write a script in Python, and that Python script would be submitted through presumably the GIS gateway, and then a translator would take that Python script, convert it into a C code, okay? It's actually C code with a wrapper around it. And that would be compiled, and then the program would be executed on a parallel processing architecture, and the results passed back to the user. The user actually doesn't write any parallel code at all. Okay? In fact, the user doesn't write any code at all. Okay? I've suggested that the user could participate in the process by providing some information about how he or she thinks the problem should be decomposed, either spatially or temporally, and even within spatially, different ways of doing that as well. Okay? And that's the end of my talk.